Welcome everyone. This is the second video in our series about conducted emissions. It deals with the different techniques to measure differential and common mode conducted emissions and gives a general overview about regulatory institutions. We start by explaining a vital component for these measurements, the line impedance stabilization network. Afterwards, we talk about performing measurements with different equipment before giving an overview of the regulatory standards. As a conclusion to this video, we will give a short summary of the discussed content. So without further ado, let us dive straight into the measurements. To measure the conducted emissions of a device under test, short DUT, a line impedance stabilization network, short LISN, must be placed between the power supply cords and the device under test. The LISN establishes a well-defined impedance between the power supply and the DUT, and therefore compensates for differences in the power distribution network, including different noise levels from other electronic devices. The LISN is therefore essential to make such measurements repeatable. The fundamental building blocks are shown here. Such a LISN consists of a low-pass filter placed between the device under test and the power supply, and a high-pass filter connecting the DUT to our measurement instrument, in this case an EMI receiver. The high-pass filter blocks low-frequency components from reaching the measurement instrument. Thus, together with the low-pass filter, which blocks the high-frequency components from the DUT, as well as potential noise signals coming from the power supply, we only receive the desired high-frequency conducted emissions on our measurement instrument. This ensures an unaltered measurement of the conducted emissions for different measurement setups. The blue and red arrow indicate the paths taken by the supply signal and high-frequency signal, respectively. Furthermore, it is important to note that there may be differences in the architecture of the LISN depending on the application-relevant standard. Here you can see a so-called two-path V-LISN. This LISN provides a symmetrical load on both power lines of the DUT. The inductors on the left are placed to block high-frequency components, while the resistor and the capacitor between the power lines and ground provide a path to filter out the noise from the respective power supply. On the right side of the DUT, capacitors are utilized to block the low-frequency components, followed by two 50-ohm resistors, one being the input resistor of the measurement instrument, and the other one is a dummy resistor for symmetry. The 1 kilo-ohm resistors are placed to provide a path for the capacitor to discharge. The typical impedance of the presented LISN over the measured frequency range is 50 microhenry plus 5 ohm in parallel to 50 ohm. Typically, this impedance is stated in the datasheet of the LISN. Now that we have established the functionality of a LISN, we want to shift our focus to the measurement equipment. The obvious choice when measuring emissions would be an EMI receiver. However, as it is quite expensive, many standards also provide a guideline on how measurements can also be carried out with a spectrum analyzer under certain conditions. If you are not familiar with these measurement instruments, please visit our dedicated videos. We will explain the necessary settings based on the current CISPR 25 standard, which is a European standard commonly used in the automotive industry. This standard regulates frequencies from 150 kHz until 108 MHz when measuring conducted emissions. For setting up our measurement instrument, we must further distinguish between frequencies above or below 30 MHz. This is necessary as at 30 MHz we move from the so-called frequency band B, ranging from 150 kHz to 30 MHz, to band C plus D, ranging from 30 MHz to 1 GHz. Now, setting up the EMI receiver for frequencies below 30 MHz is straightforward. We start by adjusting the frequency range in the scan table. The resolution bandwidth and step size are by default set to the corresponding values of the respective bands. For band B, this means that the resolution bandwidth is 9 kHz for all detectors, while the maximum step size is 5 kHz. We then set the minimum dwell time to 50 milliseconds for the peak and average detector and 1 second for the quasi-peak detector. In case of the spectrum analyzer, we also start by setting the start and stop frequency. Afterwards, we have to manually set the resolution bandwidth to the required 9 or 10 kHz in case of peak and average detector, and 9 kHz in case of the quasi-peak detector. Note that the resolution bandwidth requirements are different based on the used detector, and not every spectrum analyzer may offer all detectors. As there is no dwell time in case of a spectrum analyzer, the next step is to set the minimum scan time based on the displayed frequency range. In case of the peak and average detector, we must choose at least 10 seconds per megahertz, while for the quasi-peak detector, this increases to 200 seconds per megahertz. Also, for both frequency bands, the video bandwidth must be at least 3 times the resolution bandwidth. For frequencies above 30 MHz, the same setup procedure must be followed. We start by adjusting the frequency range for both instruments and set respective dwell time for the EMI receiver and resolution bandwidth, as well as scan time for the spectrum analyzer. Note that when using an EMI receiver, both frequency bands can be measured in one run if the settings for both are added to the scan table. This is not possible when using a spectrum analyzer. With that said, let us briefly talk about the regulatory institutions and their respective standards. There are 2 prominent institutions when it comes to measuring conducted as well as radiated emissions, the FCC and the CENEEC. The FCC operates in the United States of America, while the CENELEC regulates the European market. Both institutions provide a variety of different standards depending on the field of application of a device. Most of these standards are based on regulations developed by the CISPR, a committee specializing in regulating electromagnetic interferences. The process of complying to these regulations depends on the regulatory authority. In the EU, for example, it is usual to perform compliance measurements at an accredited test house. Let us recap on what we learned in this video. In order to perform repeatable and meaningful measurements of the conducted emissions, a line impedance stabilization network must be placed between the DUT and the power supply. When it comes to choosing the measurement equipment, an EMI receiver would be the preferred choice. However, under certain conditions and with some extra steps, also a spectrum analyzer may be used. When it comes to regulations and standards, there are differences depending on the market as well as field of application. Also, the process of compliance varies.